biped. But if Michel is right, his 6-million-year-old fossil is a good candidate for the first human ancestor. Discoveries like this are changing the way we see human evolution. Scientists used to have a simple idea. The growth of open grasslands forced our ancestors out of the trees. They became bipeds, and in short order, brain size increased. Human evolution took off. We were on our way to becoming human. That simple idea prevailed for more than a century.
Darwin thought that we left the trees, walked on the ground upright, freed our hands, made tools, got big brains, reduced our canines, and so on, all at the same time.
But walking upright may not have automatically led to big brains at all. From Human-Part to Selam, both bipeds, brains stayed small. And they weren't the only ones. Over millions of years, there was a profusion of upright walkers with complicated names and chimp-sized brains, like Auroran tuganensis.
What we're seeing is a fluorescence of species, multiple species. They're probably subtly different from each other.
Ardipithecus ramidus.
But it's important to recognize that there are not major differences among these species.
Australopithecus africanus.
They were all bipeds, big snouts, more or less chimp-sized brains.
Kenyanthropus platyops.
This way of life, this suite of adaptations, lasted for millions of years.
Small-brained bipedal apes were extremely successful. Debates rage among scientists about which one eventually led to us. But as a group, they flourished for about 25 times longer than we've been around. They survived and thrived as brain size flatlined for almost 4 million years. But that doesn't mean nothing changed. There's evidence that the seeds of our humanity were growing in these ape-like creatures. One key difference between humans and apes is the length of childhood. But what do we know about the childhood of our early ancestors?
We know all about the adult individuals, but we didn't know much about the children.
The brains of baby chimps have an early growth spurt. They're almost fully formed by age 3. In humans, that growth spurt is slower, and it takes nearly 2 decades for our brains to fully mature. But what about Selam's brain 3.3 million years ago?
But of course, most exciting.
Her skull tells us all we need to know.
At this place, this
We have her milk teeth
tells you.
and her adult teeth, which give us her age, 3 years old. And we have a cast of the inside of her skull, which tells us about her brain.
When you have this, you can directly measure how much of the brain was formed at age 3.
From other fossils, we know how large Selam's brain would have been as an adult. So Zeray could calculate how much of her brain was already formed by age 3 when she died. He knows what the answer would be for a chimp.
By age 3, a chimpanzee would have over 90% of the brain formed.
But Selam's brain was only around 75% of its adult size, suggesting it was growing up slower. Childhood would have been her time to learn the survival strategies her family group needed to live in a dangerous world. Perhaps this set the stage for our longer human childhood, when culture is handed down. But is there any other evidence Selam's brain was becoming more human and less ape? To find out, compare a human brain to a chimp's.
This is the brain of our closest relative, the chimpanzee brain. It's slightly larger than you would expect of a typical primate for their body size, not greatly so. But there's a difference.
Scientists look for clues to the evolution of the brain in the folds and furrows on its surface. One important structure is called the lunate sulcus.
In chimpanzees, as in many primates, there's this big, deep sulcus here, the lunate sulcus.
The lunate sulcus is a deep furrow in a primate's brain. It divides parts of the brain related to vision from the rest of the neocortex, which is where more complex thought happens. The human brain doesn't have this deep furrow, and the neocortex is bigger than the vision structures, which have moved far to the back. So did Selam have the deep furrow and small neocortex of a chimp, or had something changed? Brains don't fossilize, but her remarkably complete skull provides a way to see some of the different structures of her brain. A cast of the brain case, called an endocast, preserves the impression of the brain's surface. Ralph Holloway has a collection of 300 brain endocasts from many of our ancestors.
What a paleoneurologist like myself will be looking for are those indications on the endocast that might suggest reorganization taking place. And that's why things like the so-called infamous lunate sulcus becomes important.
Ralph claims that as chimp-like ancestors evolved into creatures like Selam and Lucy, the lunate sulcus, the furrow marking the vision structures, moved back, making room for a larger neocortex, the thinking part of the brain.
If you look carefully, what you've got here is a depression that could very likely be the lunate sulcus. And so that suggests then by Australopithecine times that you're having a beast that is simply smarter than present-day chimpanzees.
If that's the case, although still the size of a chimp's, Selam's brain had been rewired. But there was a long way to go. She and her kind were still very ape-like. It would take another 1,000,000 years for the seeds of humanity contained in Selam's tiny frame to bear fruit. It's a time still shrouded in mystery. For almost 500,000 years, the fossil record is virtually silent. But in this blank period, something is happening. In 2.5-million-year-old layers, scientists begin to find something new. We might be tempted to call them rocks, but someone was shaping them. They are the first stone tools.